Okay, so this lecture is going to be on physical pendulums. They're a lot like the simple pendulum, but, well, not quite as simple. They can actually get fairly complex. So, generally the setup is kind of similar. You have a ceiling or something else. Actually, no, let's not go with a ceiling in this context. It's better to think about it in terms of you have some object with some kind of shape to it. Just some arbitrary shape. And it's going to have a pivot point. So we'll set the pivot right here. And then it will also have a center of mass. So there will be a distance in between those 2 points, and call that XCM. And of course we'll be talking about it pivoting around here, having some vertical axis that makes an angle. One thing that is the same is the only force that's capable of creating a torque will be the gravitational force. So we will again be thinking about gravitation along a couple of directions. And the torque due to gravitation is going to be a minus XCM, because that's the distance to the point of application of the force, times the force sine of theta. Okay, so it's going to be very similar in that respect. Okay, and oopsies, I kind of want to make this picture bigger, just so it's easier to see. Okay, so the same thing will be true about the sum of torques will be equal to I times alpha. The thing that's now complicated is determining ICM and possibly determining the net force. We will actually be doing a problem with 2 objects connected together as an example. And when we talk about that, I'll show you how you can think about, well, you can do the sum of torque due to object 1 and object 2, and the distance is applied to each, and you'll get the same result as finding the XCM using the formula from your 1A class, and thinking about the total mass for the total gravitational force. The general gist, we're going with this for now. So we'll have minus XCM times m times g sine theta is equal to I times alpha. So nothing too different so far. The main difference is I is no longer something that we can automatically write down. So we'll have to take it to our standard form as best we can. Oops. Sine theta equals 0. We have the same limitation. We can really only solve this. So we're still limited to small angles of release. When you finally have your differential equations class, you will learn a little bit more about this type of equation without the small angle, where you still have the sine theta. And generally it's not something you are happy to see because it's a non-linear differential equation. And those tend to be much, much harder to solve, if they can even be solved, in a closed form. You can still set up the equations for it and do a simulation where you do a numeric trick. That can still be done even if the differential equation can't be solved, and that's probably where you see some of the weird trickery with double pendulum simulations running around out there in the wild. Okay, so if the angle is small, however, then we get alpha plus the center of mass distance, the distance from the pivot to the place where the force of gravity is effectively applied, times m times g over the moment of inertia, times the angle theta gives us that. Again, we know approximately what this should look like. Theta will be some function of a cosine of omega t plus phase, and as usual we'll be able to break it down to minus omega squared Then the plus xcm mg over I equals 0, which means omega is the square root of the distance from the pivot to the center of mass times the weight divided by the moment of inertia for the shape around that pivot point. But here's the thing. Don't memorize this. What you really want to do every time you're doing a physical pendulum problem is think about it just as it is. Come back up, draw your shape out, locate its center of mass, locate the pivot point, think about the distance between them and identify it. If it consists of multiple shapes connected together, we'll find the distance from the pivot to the center of mass of each of the shapes individually. Find the torque due to gravity for each of the shapes individually. And then add up all the torques for all the pieces that make up the shape and set that equal to the total moment of inertia for the whole shape times alpha. So for each one of these, you want to find the torque for each of the pieces around the center, well, around the pivot point. Then you want to find total torque due to gravity. Find the total moment of inertia about the pivot. And then calculate your result. This avoids a lot of issues where you might make mistakes, because what if you make a mistake in finding xcm? Remember, xcm is something that goes as the sum as x times mass divided by the sum of all the masses. You don't want to make a mistake doing that and get things wrong part way. M in this formula up here is the total mass. If you do the process that I'm describing down here, you're not going to ever make that mistake. You'll always have the right total mass. Moment of inertia is still a problem, but it's going to be a problem no matter what. You're going to have to find the moments of inertia of each piece that makes up the whole thing and get your result that way. So oops, I equals 1 to n. So when I'm doing my examples, I will be doing the examples step by step, stage by stage. I'm always going to come back up, draw my picture, go through things carefully, and find my omega or whatever else I need, step by step. It's the process that you want to understand here, because the process never changes. Whereas how you apply this equation, you have to be super careful not to make mistakes in application. Okay. Let's see. I guess since we kind of know what omega looks like, we can talk about the period, which would look like 2 pi square root of, as always it inverts, because if omega is equal to 2 pi over the period, then the period is equal to 2 pi divided by the omega. Okay. So that's it for right now on physical pendulums. We are going to come back with 2 more example problems that I will be doing as videos, and we'll do at least 1 or 2 more in practice sessions. So you will get to see more opportunity how this works in practice. Alright, that's going to be it for this time. And onward to next.